So we talked about this boundary condition last time, q dot s equals constant, and we saw how you can find out T at the exit. If you have some information about the flow characteristics, this is about TE, this is about TI, and what those TE and TI are, they are mean temperatures, okay? And a very specific point about that mean temperature is that you would find out that it is varying as you move along x, even in the thermally fully developed region, okay? But this does not happen for V average. V average remains constant in hydrodynamically developed region. Now, then we moved on to a condition where Ts was constant, and there we found out that we can describe the mean temperature variation, or let's say T at the exit, by what? Logarithmic mean temperature sense. This is the approach which you should use, okay? So, and you have seen the variations as well. In one case you have a linear variation, and in that case surface temperature also varied with the same slope, but as far as Ts is equal to constant, you have to go for this thing, and this you have already studied in flow over tube banks. We just discussed that thing, and then I proved it during the last lecture. So now just few points about the CF and Nusselt number. Till this point we were just talking about Tm, Te, what are the qualitative parameters which are associated with this pipe flow. But now let's start discussing the correlations which are there to find out friction coefficient and Nusselt number, okay? And we would be looking for all those relations which may be, you can say, which might have been applied to the laminar regime, then the transitional regime, then the turbulent regime, okay? These are the three regimes which you can consider, and then it depends on the shape of the body as well, the shape of the pipe, the cross section. So just few things I would remind you, and you can see the derivations from your fluid dynamics notes. I did those derivations during that class, so I am not going to repeat it. So laminar flow in tubes, I would write down those relations, that in this case dP by dx, this pressure gradient, that is equal to minus 2 wall shear stress over R. Does it look like familiar to you guys? You should have seen it, okay? We have proven that in fluid dynamics course. And then we found out the velocity profile, which was the proof of that parabolic velocity profile, that was equal to minus r square over 4 mu dP by dx 1 minus r square over r square. So this is something, the quadratic profile, which tells you that the velocity profile would be kind of parabolic. Okay. Similarly, for a circular pipe, and I am just talking about tubes. Remember, whenever I am talking about tubes, generally they are taken in a sense where you have circular cross-section area. Okay, tubes, small diameter tubes. So circular cross-sectional area, that velocity profile is only applicable to this one. So for the same circular cross-sectional area, we have V average. Just apply the definition which we have seen earlier during the last lecture. V average is equal to minus r square over 8 mu over dP over dx. Remember, I am not doing the derivation because I have already done that in fluid dynamics course. Okay. So this was V average. And U of R can also be written as 2V average 1 minus R square over R square, by just plugging those numbers back into this U of R profile. and the Umax was equal to 2V average. And this is only true for circular tubes and that with laminar flow. Okay. Now, again by repeating few of the relationships for the same case, laminar flow inside a pipe or inside a tube, this delta P was equal to 32 mu L V average over D square. You have been using this relationship, right? And if you remember, we got it from the analytical solution, and I told you there is another approach where you can use an empirical approach to find out delta P, pressure drop or pressure loss. That pressure loss can also be written as F L by D rho V average square over 2. And what is this F? This is the friction coefficient, but which one? This is the Darcy friction factor. Yes, this is the Darcy friction factor, and it is different from CF. CF is something which is known as Fanning friction factor, just named after the scientist who used it. Fanning friction factor. And what is the relationship between them? CF is equal to F by 4. Okay. Under the same topic, we also talked about this relationship that for laminar circular tube flow, the same case which I am talking about, F is equal to 64 mu over rho dV average, and that was equal to 64 by RE. And then the head loss, basically the head loss is something which is there to maintain a certain height to counter those frictional effects inside a pipe. Okay, so this head loss is there, and that was equal to F L by D V average square over 2G. And then we also found out the pumping power, which was equal to m dot G HL. And these relationships are true for which flow regime, which cross section? Okay. Does it look like familiar to you? We talked about that relationship. There is something which was derived by this scientist. Okay. So, because those things are only related to the previous fluid dynamics course, I have only given you the relationship just to remind you of those things. You can see the derivation once again. You just have to revise it. If you still have any question, you can ask. But we were generally interested in friction. And why friction? Because we have to take care of the friction by putting more and more pumping power. Okay, so that's why we discussed those things. And then let's talk about the temperature profile and the Nusselt number. I am just using the same headings as given in your book so that you do not have any problem in tracking those things. So temperature profile and Nusselt number. There was an energy balance. If you just take a piece of pipe, let's say a simple piece of pipe, just because of my bad drawing skills, I am using this kind of cross section. You might have seen a three-dimensional section in your book. Okay, So if you just look at that section, this is something which is dx. Let's say a flow is coming into this portion. Obviously it has certain m dot. The same m dot would be going outside it. So this is inlet. Let's say this is a small portion, and these two are just describing the inlet and the outlet section of this pipe. Now you know that due to this mass flow rate, some heat would be transferred. You remember that Q dot was equal to what? Okay, so some heat is being transferred by this mass flow, right? And then this is the pipe wall as well. Let's see. This is the pipe wall as well. Okay, so some heat would also be conducted through the pipe. For example, if you give Ts at its surface, that heat would be conducted to this surface first, and then it would be convected by the fluid. Okay, so there are two types of heat transfers, one due to the mass flow rate and the other due to the conduction. So okay, so heat transfer due to mass flow, and the other part is heat transfer due to conduction. Just see, obviously there would be no heat generation inside the pipe, right? We are not going to store any kind of heat as well. So whatever is coming inside this pipe, that has to be taken away. Okay, so there are two mechanisms. This heat is being taken away, or let's say this heat is being transferred by this mass flow rate, for example if the temperature is different. But how is that difference coming from? So that difference is coming from this boundary condition. If you put some other temperature, let's say some temperature other than the fluid temperature, then this heat would be transferred, isn't it? If Ts and Ti, T of the fluid are equal, there would be no heat transfer, right? So this Te is different from Ti. Why? Because of this different temperature than the fluid one. Okay, so this is the point. So there are two kind of mechanisms in a pipe where you can, and in this case I am just disregarding the heat which is being generated by the friction, right? I am just disregarding it, that the heat generated by the friction, that is not being considered over there. You can also, but people have checked that and it has a negligible portion inside a pipe. If you consider frictional heating, it is very low. Okay, sorry, no, this is something which is there due to convection, isn't it? You are talking about that Newton's law of cooling, but that has been taken into account by this relationship. Okay, there are two mechanisms, how the heat is coming in and how the heat is taken away. The heat is coming in due to the different temperatures of the fluid and the surface, and the heat is taken away by what? That mass flow rate. Okay, so I would just write down the relationships once again. If you do this kind of energy conservation principle on this pipe, you would come up with this relationship. This is the final equation which I am going to write down. This is the final equation, just 2-3 steps. You can quantify this thing. Once it is entering through this thing, you can write it like m dot Cp Ti. Then this can be written as m dot Cp Te. If there is small distance and this section is x, you can just consider their temperature inside. Instead of using Ti, you can say it is T of x. For this thing, you can write Te equals T of x plus dx. These are the notations which have been used in your book, right? So heat transfer due to conduction is always governed by the Fourier law. You can write down those relationships as well. But this is the final equation which I am interested in. Okay, this is the final equation to find out the temperature profile inside the pipe fluid. So again, there are two conditions. We have to look upon those two conditions. One is constant surface flux. that says partial T by partial X is equal to constant, and I would write down the final relationship, final solution for this one. The final solution for a circular pipe is T equals Ts minus Q dot S R over K 3 by 4 minus R square over R square plus R4 over 4R raised to power 4. This R is the maximum radius, remember that. This capital R is the maximum radius. So this is how you can find out the temperature profile inside the fluid. Similarly, if you use the mean temperature definition, you remember that we talked about the definition of this mean temperature profile. Sorry? Yes, flux, boundary condition. If you talk about the surface, surface is along what? X. So Tm, if you use the same definition where we use something like, if you remember that, T of R and then we have like D of R, something like that, we derived that thing. So if you use that definition, Tm comes out to be equal to this one. Okay, this is the mean temperature which you can find out for this constant surface flux condition, and the convection coefficient would be equal to 24 by 11 K by R, and that comes out to be equal to 4.36 K by D. And if you find out the Nusselt number, that Nusselt number comes out to be 4.36. So you can say in a laminar flow, you see Nusselt number remains constant. That's what we talked about for a thermally fully developed region. You remember that we talked about that H, how it remains constant. So analytically you have found almost the same thing. Okay, we took another approach while proving that thing, why it remains constant in the last lecture, but this time you have seen another route by applying the energy conservation principle, a steady state case onto a pipe portion, then through those definitions of Tm, you have come up to the same conclusion that H or Nusselt number remains constant inside the pipe once you are in the thermally fully developed region. The second condition is constant surface temperature condition. In that case, Nusselt number comes out to be 3.66, and remember this constant surface temperature condition, this relation is not from analytical solution. This has come from numerical experimentation because the equation becomes too complex to handle analytically. Okay, so again you can see that in a constant flux condition you have 4.36, in a constant surface temperature condition you have 3.66. So that was about the Nusselt number. Let me show you a table where we can talk about laminar flows in non-circular conduits. You can see that all the conditions are given in that table. That table is 8-1 given in your reference textbook. You can see tube geometry is given. In some of the cases you have aspect ratio as well. This is A by B, where aspect ratio is something like width over height, something like that. So A by B, if you have these numbers, you can see what should be the relationship to be used in certain condition. Okay, and almost in all of those conditions they are constants. And remember, all of those relationships or numbers, they haven't come through analytical techniques. Most of the time they have come through numerical techniques or numerical simulations or real-time experiments. So this is the table which you should use according to the system which you are studying. right? Then again, because I talked about the laminar fully developed regime, let's talk about developing laminar flow in the entrance region. In that case, one relationship comes for this flow, that is Nusselt number equals 3.66 plus 0.065 d by L Reynolds number Prandtl number over 1 plus 0.04 d by L Reynolds number Prandtl number raised to power 2 by 3. Now you see, in the fully developed regime it was 3.66 only, but now there is some additional factor. You remember this plot where we talked about H, which was greater in this region, you see? So that increase in magnitude is taken care of by this factor, right? So this relationship should be used when Prandtl number is greater than 5, right? And most of the time those fluid properties for Reynolds number and Prandtl number, they are found at bulk mean temperature. And what is that bulk mean temperature? Okay. Now again, there is another limitation, that this relationship should be used when Ts and T infinity, the difference is not much larger. T infinity, I am considering that T infinity not in the free stream sense, but the temperature of the fluid. Let me write down this temperature of the fluid. When Ts and T infinity are not very large, this is small. When this difference is very large, you should use another relationship, which is Nusselt number equals 1.86 Reynolds number Prandtl number d over L 1 by 3 mu b over mu s 0.1 by 4. I hope you understand what does that mu b means. Mu b means viscosity found at bulk mean fluid temperature, and then mu s means viscosity which is found at surface temperature. Okay, so this is the relationship which you should use when Ts and Tf fluid, their difference is large, right? Large means considerably large. You cannot quantify it. Like for example, if the difference is like 10 to 20 degrees centigrade, you might be using the first relationship. If it is more, again it is debatable. It is always debatable. What should be the extent where you should use other terms? So in the next class I would start the natural convection portion, inshallah, right?